third topic of this course is about data acquisition. And just a short reminder what it's all about. I have a short slideshow here. So practically we are talking about a digital signal properties, and as an example there would be a voice recording process. Although I would guess that in your case you will be mostly using these the data acquisition system for some sensor data, but anyways this is just a example to illustrate what is happening. So for any signal in real world, actually you probably first need an analog gain to get the signal a little bit bigger, to get better resolution, or actually take most out of the A to D conversion. After that you should have some sort of anti-aliasing filter followed by sample and hold, and then actually you do the A to D conversion. Modern A to D converters actually have these are usually common. The sample and hold and A to D conversion is made in the same device. Okay, if you take a look at the signal with the oscilloscope, what it looks like, it and the beginning actually on here it's a small signal with some noise on it. After the gain block, it's bigger signal, it still has that noise on it, and then basically it's also after the gain amplifier you should also have the level shifter to shift it so that the A to D conversion range is good for the signal. Reminder that, for example, sound is usually a bipolar signal, meaning varying on both sides of the ground level, but A to D converters usually they have a unipolar input, meaning that the input is can vary only between plus some voltage and ground. Okay, on the next step it should be cleaned for too high frequency noise, and then actually the sampling happens here on the sample and hold circuit. There basically you are stopping the signal for the duration of the A to D conversion, and then basically after the A to D conversion what it does, it also gives you the small difference, which is the quantization. So after A to D converter basically you have the sampled signal at certain bit representation. Okay, so we start with the analog signal, which is continuous in time and continuous in value. Then the sampled signal, which is discrete time but still continuous in value. And finally the digital signal, it's discrete time and quantized value. Okay, so about the sampled signal, basically signals are generally sampled with constant sampling rate. That helps a lot the analysis of the signal. You should know that if you have taken the digital signal processing class, why we actually should be using the constant sample rate. And then the sampling time interval actually is just the 1 over the Fs. And okay, Shannon's theorem, you must take at least 2 samples per original signal period. If you don't have enough of samples, meaning the sampling frequency is too low, meaning too long sampling interval, then that can lead to signal aliasing, and this is what happens. The blue one is the real signal, and if you take samples there on those marked points, then you end up having something else. So it looks like sinusoid, but it's totally corrupted, since basically it gives you wrong impression of the original frequency. Okay, then back to the digital signal, so sampled in time and quantized in value. So in the digital signal processing, actually the quantization error can be considered as some extra noise, which also limits the A to D converter result. So basically, then you have the signal to quantization noise ratio, which tells you how many bits actually you need in order to get enough of signal. Okay. An example on that one. So basically, audio signal, so human ear can detect signals roughly between 20 Hz to 20 kilohertz. So that means that Shannon says that you need at least twice the highest frequency, so 40 kilohertz sampling rate for good audio recording. Okay, so it's not coincidence that if you have a old-fashioned CD quality PCM pulse code modulated signal, it actually has this 44.1 kilohertz resampling rate. It can be higher, and modern recordings actually have higher sampling rate, but for different reasons. Basically, that's because if you have a higher sampling rate, then you can start you can actually pack the bits a little bit more efficiently. Listening music actually requires normally sound pressure levels in range of 20 to 100 decibels. Okay, 20 decibels, the decibels on atmospheric pressure is actually so small that you barely can hear it. So this is something, a level that is already humming on your ear when your blood is circulating on your ear. So you get about 20 dB from that one. 100 dB is when you are starting to hurt your ear. So 100 dB you can still tolerate on peaks, but not for continuous signals. Okay, so in order to make recordings, the signal to quantization noise ratio should be more than 80 dB. So it's just 100 dB minus 20 dB. So we need at least 13 bits resolution, and wow, the CD quality PCM signal actually has 16-bit resolution. So that should be enough. So CD quality signal, the signal actually should be good enough for the high quality audio signal. And you need only 16-bit resolution for that. Okay, some recordings are actually, the professional recordings are made with 24-bit, but that's because of the dynamic range. It's easier to handle the dynamic range when you add bits. Okay, then just a reminder of this signal to noise ratio, the true signal to noise ratio. So that is actually defined as the power of signal divided by noise in noise power in decibels. And I think that is actually all I had to say. So what you remember from here, okay, practically this one here. So you start with a small signal. You need to amplify it as much as possible, but not more than that. then make sure that you are not aliasing. One way to actually assure that the signal does not alias is to oversample it. So you have much more samples than you need at the highest rate, and if you are using, for example, a sigma delta type of the A to D converter, then you practically have a really difficult time of having aliasing effect there, even if you mod it. So the sigma delta is actually the integral part of sigma delta is doing the sampling and holding quite well, so that it takes off these two high frequency noise. Okay. So that was overall the about data acquisition. There are some useful links again. Okay, how to select analog ground and reference. Oh, okay, don't use that one. That's actually for PSoC1. I will try to find a replacing the link for that one. So if it's still there, the PSoC1, don't use it. Okay, I will stop this recording and go and start a new one for this exercise part.